All right, we're going to look at these last three examples from our class notes from section 1.1. So for all of these, we're given a differential equation. So I'll just give you a second to look at those. You should notice that they're all first order ordinary differential equations, and they are all three non-linear differential equations. We're given a solution for all of those, possibly a general solution. We really need a theorem to know for sure if that's a general solution, but it is a solution that represents a family of solutions because they all have a parameter in them. And then for all of these, we're given an initial condition. So we're going to find the particular solution that satisfies the initial condition and then think about the interval of existence of that solution. So I'm going to zoom in a little bit here. All right, so to find the particular solution that satisfies the initial condition, we're just going to put in the values for our variables for x and y. So we'll have 2 equals 1 over c minus 0. So you do a little bit of algebra there and you'll get c equals 1/2. That's pretty straightforward. So the particular solution that satisfies the initial condition is this. You could do some algebra simplifying if you want. Multiply through by 2 over 2 so that you can end up rewriting that as 2 over 1 minus 2x. So either of those are the same. They're both perfectly fine. MyMathLab should recognize either form of something like that as the same thing. And then the other thing that we want to think about here is the interval of existence of this solution. So this solution, unlike the previous one, does have a discontinuity. So this function here is only continuous on the interval -infinity to 1/2 or the interval 1/2 to infinity. So not continuous at x equals 1/2. And remember that in order for a function to be differentiable, it must be continuous. So if the function is not continuous at x equals 1/2, then it can't be differentiable there. We also might want to look at the differential equation and make sure there's no other things in the differential equation besides just looking at the solution that would cause the solution to not satisfy the differential equation at any particular value of x, but there aren't any others for this one. So one of the mistakes that students often make about interval of existence is that they will write down both of these intervals, or the wrong one, perhaps. The important thing to understand here, though, is that we are given a point at the beginning, and our point at the beginning here is at x equals 0. And x equals 0 is in this interval here because 0 is less than 1/2. And so since x equals 0 is in that interval, this is the interval on which this solution exists, and it can't jump across that discontinuity and still satisfy the differential equation. So the interval of existence for this solution and this initial condition is -infinity to 1/2. And again, that's an interval of values for the input variable, the independent variable, for which the solution that we've got satisfies the differential equation and the initial condition. All right, so let's look at this next one. Notice it's the same differential equation and we've got the same general solution given and we've got an initial condition here. So we're going to start by just doing the same thing we did before. We're going to put in x equals 0 and y equals 0. But on this one, something strange happens. So this is not true for any value of c. So what that means is that although this solution satisfies the differential equation for some initial conditions, like in the previous example, that solution does not satisfy the differential equation for all initial conditions. There is no value of c for which that solution curve would go through the point 0, 0. Remember that these initial conditions really are points that the solution curve would pass through. All right, so the issue here would be that if there is a solution to this differential equation, it does not satisfy the form of this general solution that we're given here. And this one is a simple enough differential equation that you might be able to think about a function whose derivative is the same as the square of the function, and maybe just by looking at it, we will talk about how to find these out if you can't do it just by looking at it. but you just by thinking about it, you might figure out that the constant function y is always 0. The constant function y equals 0 satisfies this differential equation, right? The constant function y equals 0, its derivative is 0, and then when you put that into the differential equation, you get 0 equals 0 squared, 0 equals 0. That checks. So it does check in the differential equation. And so this is a function that does satisfy the differential equation, and it does pass through the point 0, 0. So this would be an example of what we talked about in the vocabulary as a singular solution. We will talk in section 1.4 about how to find singular solutions and think about, how do we know if we might have one or not. We'll look at some theorems and some techniques. But the basic idea here is just to provide a little bit of an example of something where you have a solution. It does satisfy the differential equation and the initial condition, but it does not fit the form of the general solution. It doesn't work for any specific value of c. All right, let's look at this last example here. Notice in this last example that we had from our class notes that the solution that we're given is actually an implicitly given solution. It's not solved for the dependent variable y, and in fact you really can't solve it for y. The algebra doesn't work because you've got a y inside the logarithm function and then this other term that's just x times y. So you can't completely isolate the y on that one. Notice on the other ones that the solutions that were given were solved for y, so those were explicit solutions. But we still can find perhaps a particular solution that satisfies the initial condition. So we'll just go ahead and plug these values in for x and y. So on the left side we'll have x times y, so 2 times 1 equals ln of y is 1, plus c. So we get 2 equals natural log of 1 is 0, and so the right hand side is just c. So c is 2. All right, so this is the particular solution that satisfies that initial condition. We might think about our interval of existence for this solution. This one's a little bit harder than the other ones we looked at because it's hard to think about where this function is differentiable and what intervals of x values might make that happen. So I'm actually going to look at a graph to think about that. So I'm going to pull up Desmos here. All right, so I've gone to Desmos and I've just typed in my equation xy equals ln of y plus 2, and it will graph implicit curves for you. So I just graphed that, and we see that we've got this function here, this graph here, that's not really even a function. It doesn't pass vertical line test, so it's not really even a function. And I might think about the initial condition that we were given. It was y of 2 equals 1, so that is a point at 2, 1, which would be right there, 2, 1 approximately. I can't get it to be exactly right there, but 2, 1, there we go. Oh, I had it there for a second. 2, 1. Right there's that point. So the part of the solution curve that we actually are on, where we satisfy the differential equation, would be this top part. And so when I think about the interval of existence, I want to think about where this would be differentiable. And you might notice over here on the right hand side, Desmos has kind of identified this point for us, 2.718, 0.368. That point appears to be about at approximately x equals e. And so when I think about the interval of existence for the solution that I was given there, we need to think about, I'm just going to draw a little sketch of that curve over here. It was sort of like that. And this point here was approximately at x equals e. And the y coordinate maybe is a little bit harder to recognize. It might not exactly be at e, but it appeared to be that. And the initial condition that we were given, 2, 1, was on this part of the function. So the place where the solution curve would satisfy the differential equation would be this region here at the point that appears to be approximately x equals e. The function appears to have a vertical tangent line, and certainly beyond that point the graph isn't even really a function, so we really can't talk about derivative beyond that. So when I think about the interval of existence from looking at that graph, it appears that we're looking at some interval here where x appears to be between 0, and e, not including 0, not including x equals 0, and not including x equals e on that branch of that solution curve. So from the graph here on this one, it appears that the interval of existence is approximately 0 to e based on our graph. And so we might look at that, some more evidence, when we think about some theorems and think about where we know that a solution might be guaranteed to exist or not. And so we'll look at some theorems later in the chapter about that. I think I forgot to mention interval of existence on this previous one. Remember that this is a constant function. If I want to think about the graph of that function, that's just the constant function, y equals 0, the line. That function is continuous and differentiable everywhere. And if I look back at the differential equation, and I think about that function, there's not going to be any places along there where we're going to run into any trouble satisfying that differential equation. So the interval of existence on this one is -infinity to infinity. All right, try some homework.